Okay, so I'm going to talk about plans for the project to do crowded field processing. So I think the best way to get everyone on the same page as far as what do I mean when I say crowded field processing is to just kind of hit the next slide. There we go. To stare at and kind of take in this image from the DECCAM plane survey. I just kind of picked a random medium-ish density field out of the survey that really covered the entire galactic plane visible from the south. And I think I can make two kind of emotional arguments here, which I'll try to back up later in the talk. One is that there's a ton of Milky Way science in this image. There's a lot that we can learn by actually processing the Milky Way disk really well. And the second point is that this is a different regime than we've been talking about so far, than we've been thinking about in the high latitude regime. And it sort of has different constraints, and it has different assumptions that make sense. And so it benefits from having a sort of processing that's dedicated to extracting information out of this image. So back that up a little bit more. I'll do it this way. I think it's worth just reiterating that Milky Way science is integral to LSST. It's one of the first science pillars that was in the original science book when the survey was proposed. And it's really true that this is all of the Milky Way, not just the high latitude stellar halo. The sort of state of Milky Way today is trying to understand how the different components of the Milky Way interact. And there's been a lot of value in surveys that have processed the Milky Way uniformly and been able to look at all components all at once. Another aspect that another science case that this is on is that galactic transients occur where the stars are. And so to fully explore the transient sky, as the science book describes it, we need in the Milky Way disk. And we normally say that the primary way for extracting this sort of transient information is through image differencing. And the project is committed to doing image differencing all through the plane. And we've said that for a long time. I think a lot of that science was strongly complemented by having a deep, well-measured direct photometry of those same areas. So we can kind of put this all on the same basis. So we've of our current pipelines in high latitude, in crowded fields, specifically using the DECCAPS survey that I showed you at the very beginning. And this is written up in a technical note number 77 that you can get to at that link there. First order, the predominant issue that shows up is that we just start to lose completeness in the catalogs as we go towards increasing source density. Our ability to detect closely neighboring stars just starts to break down, and we just miss lots of detections that we could be measuring. This isn't purely a sort of like core of the bulge issue. At roughly single epoch depth, 24.5-ish, say, this affects about 8% of the wide fast deep, where we would start to lose completeness. And if you think about the survey depth, it goes up to about 15% of that wide fast deep area. And this sort of, as you can guess, it's just this affects substantially all of the galactic plane itself. So as I alluded to at the beginning, they're just different things that make sense when we're trying to process these two different images. And we have, for some time, proposed that what we really want is a deblender that smoothly transitions between these two regimes, where we can have a sort of a continuously varying parameter that says, this is a high latitude field. We should attempt to deblend it in a way that makes sense for high latitude fields, that as we get closer to galactic plane, as the density of stars starts to increase, so that it knows that, okay, it's more like that things are going to look stellar-like, PSF-like, so handle those appropriately and recover as much as we can. This is like still a goal that we have. This is not a thing that we want to necessarily abandon, but it's a serious challenge. And as we've heard earlier in this meeting, there's already lots of work that needs to be done to latitude blending case. And so we're thinking about ways to kind of not have to pile another beyond state-of-the-art feature onto something that's already very challenging. And in particular, the stellar crowded field case, the solutions are already well understood. And so I think the plan that we're proposing is a way to ensure that we're able to get that Milky Way science out, kind of as a backstop for being able to evolve our deblender to a kind of fully all sky form. So, so this is just a rough outline of what we're proposing to do for crowded fields. This is written up in a technical note that you can see at the top. Number 129 has all details and down in words. But what we would do is we would start from the same coads. So this would require building a different set of coads. It would use whatever form was applicable to the high latitude pipelines. But that on one hand, while the deblending-based pipeline would produce all the set of catalogs that we normally think about and the catalogs that are listed in the DPDD that we've been thinking about mostly this week, we would also produce a separate set of catalogs, a really much more restricted set of columns and values that's pertinent specific to the output from a crowded field pipeline that would only work on stars and not galaxies, and would be primarily focused on areas of the sky where this is relevant. So we wouldn't not run the deblending-based pipeline in the field in the galaxy. It's valuable to have that as a comparison, that users, when they're coming to LSST and trying to decide what's best for their science, if they are looking at something the galactic plane, would be able to choose what set of data products is most relevant to their science case. So as I said, this crowded field branch would only fit PSFs to sources, and there'd be no galaxy model fitting. You would have to go to the deblending-based pipeline to get that. And then once I kind of make that assumption, and once I'm willing to go down that path of saying everything's got to be a star, the algorithm is well understood. This is based on DAO-FOT. It's been understood since about the late 80s and the early 90s. Because I know the PSF model, I can compute every star distribution to the counts in every other pixel over the entire image. And this boils down to a large matrix operation, which you can solve with kind of off-the-shelf sparse matrix. A lot of times when I'm talking about crowded fields analysis, people want to think, well, why not just run DAO-FOT itself? And the answer to that is that we can implement the core of the DAO-FOT algorithm much more easily than we can try and integrate DAO-FOT itself as a piece of software. And we've already done that basic core algorithm. So we have a prototype run that uses all of the functionality that the stack has in order to provide DSFs and to provide WCSs and to be able to do computations on it, and does solve this simultaneous PSF problem. Sorry, simultaneous PSF fitting problem. It's not I'm not saying that the solution is the kind of core prototype. So a lot of this, so we've heard kind of about all the difficulties associated with coads, all the difficulties at high as much to galactic plane or at low latitudes. Fortunately, almost all the benefits of all the solutions have been discussed. They also apply to crowded fields as well. So whatever route is taken in order to avoid the problems of discontinuous PSFs at high latitudes, I think that will just natively port really well to operations on crowded stellar fields also. So I'm not going to say much more about that. We essentially just piggyback off of all the operations that have been discussed so far. So what I see as the real challenge here for a survey like LSST is that we're not just trying to take a static picture of the galaxy or the sky in general. A lot of the Milky Way science that would be particularly valuable is in the stellar motions and in the variability. And so we want to be able to extract that information from this type of processing. Again, without having to resort to the full multi-fit-like process that we would have normally kind of assumed earlier in our planning process. And I think, again, the solutions here pretty closely parallel what Jim talked about yesterday, where short period coads are a way to give us this additional depth deeper into the galaxy and not entirely lose all the proper motion over the entire course of the survey. And then we still expect to go back to the individual images to fit fluxes for light curves. And I'll say more about that in a minute. So the overall flow here would be to take the cell-based coads developed from the rest of the pipeline, perform source detection and perform iterative subtraction of those detected sources in this loop here to develop really a deep list of all the sources that exist in that image. Those would then, for a particular short period coad, those would then get passed to determining the positions and motions by matching between different short period coads. And from that gives us a model of the motion of the star that we can use to go back to the individual epochs to get those what we call vaguely force source-like per epoch fluxes. The first step is really where the gain in terms of completeness comes from in doing processing like this. Because we assert that everything's a PSF, it's much easier to find the neighbors, the faint neighbors of your stars after you've subtracted off the brightest things that you've measured. We've heard some about this in the deblending talks about ways to also do this there. Again, I think this is complementary. It's sort of the same idea, and this is just a restricted version of the same type of problem. Because this all just happens on the coad, it's not particularly data intensive, so we don't need to have a tremendous volume of data to make this happen. This also has another iterative process involved at the same time to measure the PSF. There just aren't bright, extremely isolated stars ready for you to measure your PSF on in the middle of the galaxy. And so you need to subtract the neighbors in order to get those PSF wings to be clean. It's usually not too much of a problem, but it's an iterative process that needs to happen. And all of this kind of requires heuristics and tuning in order to make sure that you're not accidentally shredding stars into a million components, but then still recovering the completeness that you want to recover. So from those fits on short period, think 6 month, 12 month coads, wait for that large loud car to go away. That would give us positions at kind of these intervals along the course of the survey. Matching between those gives us the proper motion for stars. And from those parameters, I can sort of assert where I think the star should be on every epoch in those points. And that's how we would go back to the individual epochs to get the force photometry, to get the per epoch fluxes to make into a light curve. I think we would use those individual epochs in order to make a mean measurement. So people who weren't interested in knowing the full variability, but just want to know that's whatever type of star, could just get that from the mean of those measurements. Again, there's a big caveat here, which is that stars don't just move linearly on the sky. If they're close enough, parallax is a significant effect. And so this doesn't directly handle parallax. I'm thinking about ways to measure kind of derivatives of the star's position on those individual epochs as a way to get the information to go back and fit parallax kind of after the fact. This is a complicated task, and so I don't think we have a solid solution here that we're just going to require testing for us to evaluate how best to extract the proper information. So I think most of this can be summed up as there's not a kind of brand new insight into the algorithmics of this that needs to happen, but just a lot of little details really do make the difference between a code that kind of works and a code that works really robustly and at LSST scale. PSF accuracy matters. I mentioned earlier about the sort of heuristics that go into building source lists. And that's just something that requires experimentation and testing. There's some potentially interesting ideas about using machine learning type models in order to identify what detections should go into your fitting. I'm not necessarily using it for the fitting itself because that's a well-posed least squares problem, but it might be a way to help with some of the sort of heuristic type issues. Surveys of this before, in particular the DECAP survey that I showed at the beginning, they had trouble with diffuse light. So nebular emission really kind of played havoc with some of their processing whenever that came into the field they were working on. And so they had to develop novel ways to identify that diffuse light and make sure that it was handled properly. We sort of just need to learn from what people have done in this area before, I think, and make sure that it works at LSST depth. And there's also potential interactions between this pipeline that might be useful to the deblending based pipeline. So this might be a way to get cleaner background subtraction in regions where this pipeline is run that might feed back into that pipeline. But that's a pretty speculative thing that we'll get to eventually. So I'll just summarize that we have a plan for a crowded field data product. It's written up at the link that you see there. The algorithmic elements are well known and well understood and prototyped. And the challenge is really assembling a complete system that works robustly at LSST scale and really extracts all the information from the time domain as well. So I'll conclude there. Thanks.
Thank you, Colin. Can we have a round of applause, virtual applause on Slack for Colin, please? Okay, so we have a couple of questions queued up. We'll start with Mike Jarvis.
I'm not sure that mine's actually a question for Colin. I was just saying that a way to deal with this smoothly in a deblender would be potentially to have a prior on the probability that something's a star. So as you go into the disk, you get a lot more higher probability that things are stars, and that might be the method to make this a seamless transition. But I think that's more of a question for blending people than for Colin. So.
Would anyone like to respond to that who's not Colin? I can unmute, start a conversation.
I can say that has been the understanding that we've had so far in the survey. I just don't think that we've tried or been able to implement that.
Okay, Massimo.
Yeah, thank you. Hi, Colin. You know, I completely support your approach, and I think that let me say, the local coads are really a great idea. I have a question and maybe a comment. The question is, when you talk about simultaneous photometry, do you mean to simply use the same input catalog coming from the local quad to all the available images, or to simultaneous cross-correlates the centroids and the fluxes in each individual image? This is, you know, the classical frame approach.
I'm not sure about the word there, but I would say that the plan is to leave centroids fixed from the coads, or at least fix modulo measured proper motions from the coads, rather than to simultaneously fit both new positions and new fluxes at every epoch. So the information, the sort of per epoch information, would primarily be new fluxes and nothing else. Okay, okay. And on this regard, my comment is that, you know, within the TDS task, crowded photometry task force, we are performing some experiments on this kind of stuff. And we have evidence that when you compare the simple forced photometry approach with the whole frame approach, that is when you cross-correlate the centroids and fluxes on all the images, what you see is that at the faint end of the brightness level, the simple forced photometry tend to slightly overestimate the fluxes. And well, not that slightly, because we observe differences of the order of 0.05, 0.1 magnitudes. This difference is currently being investigated, and we are just checking if it is a software issue or it is something deep within the technique. That's really interesting. I actually would have expected the sign of the effect to be the opposite way around, because the individual epochs, if the positions are not fixed, the individual epochs are going to try and chase the bright noise peaks. But if you send me more about this, I'd love to read more about it.
Yeah, yeah. Probably we will use a mock catalog and check what is wrong. Thank you.
Okay, question from Jean.
No, my question was answered by the previous discussion.
Okay. So then the next question is from Tom. Tom, go ahead.
Hi, this question might be answered in the technical note, so I'll eventually get around to reading that after we're done here. But could you just comment on whether you handle blended source centroid shifts with regard to the detect, fit, subtract loop for iterative PSF fitting?
Sorry, blended source centroid shifts.
If you fit one source to a composite source of a bright source plus a fainter undetected blended source, you will shift the measured centroid of that composite model, which then if you subtract in your subsequent iterative fit means that you won't have cleanly subtracted the first model, and you sort of subtract some of that but leave a little bit of wing on one side and subtract some flux from the hidden source, which you then can't cleanly recover in the iterative, in the second step.
Yeah, okay, I totally agree with that as a problem. I have sort of swept all of that under the rug of heuristics when building a source list. I think that is like one of the principal challenges here, is to figure out how to make sure that you end up with a set of positions that are robustly positioned on the set of sources that you're going to measure. And then the measurement itself is much in practice is somewhat simpler than figuring out exactly all those sources that you're going to go measure. That's something that I've been playing with. I don't have a solution to, but it is a serious thing to investigate.
Will you be able to provide metrics? This might be completely impossible, but metrics on the iteration number that a source was detected in, so that end users can know if it was the bright source that was detected, or if this was source popped up after a subtraction. Is
that's totally reasonable at first glance, but I would sort of say that I don't think we have that level of, like, we're still at prototype stages, so I'm not quite yet thinking about exact catalog quantities to include yet. I'll keep that in mind, but we're not quite there yet.
Okay, great. Thanks.
Okay, the question now from Conrad.
Hi there. I was wondering, this is maybe a silly question, but to make the coads, you need some PSF information to decide on with what way to combine the sub-exposures, or even if you do the Kaiser route, then it gets much more complicated. So do you expect some complicated feedback loop between your cleaning of the PSF in the crowded fields and then making a better coad?
Sounds scary. Sounds possible also. I'm going to defer that to the coad experts like Jim.
Go ahead, Jim, if you'd like to reply.
Oh, it sounds, yeah, I don't think I have a whole lot to add. I don't, well.
I'm sure the answer is, I hope not.
We want to repropagate those PSFs through the co-addition process. And not, I mean, if we're using any kind of PSF information on how to weight the different coads, we would not want to revisit that at that stage. I certainly hope it wouldn't matter. But yeah, I don't think I have a whole lot to say other than, yeah, it sounds intriguing and it's not something I've thought about before.
Okay, do we have any more questions? You can either raise your hand on Slack, raise your hand, or type the question into Slack. Okay, so if we don't have any more questions, let's thank Colin again for that talk.